right, so in our study of classical physics, we learned about two really foundational conservation laws: the conservation of momentum and the conservation of energy. Now, as we started to explore special relativity, we found that things like time and space change depending on the reference frame, right? And time and space are both parts of momentum and energy. So you might start to wonder how momentum and energy are affected in the concept when we consider special relativity. And if they're affected, then do the conservation laws continue to hold? Are they truly laws, or does something change when we look at special relativity? So that's what this mini lecture is all about. It's really going to introduce you. We're not going to derive the relativistic momentum and the relativistic energy, but we're going to pull out some really fun things about how, one, conservation, yes, still holds, but we have to consider what we've learned about time and space as we explore it. So we're going to do that today, and then even a more fun thing in terms of energy. All right, so let's start with momentum. If we look at momentum, we know that momentum, remember, in the classical sense, momentum was equal to our mass times our velocity, right? And it's a vector, right? So we got to consider all of those things. But what happens when I look at it from a relativistic standpoint? When we do that, we actually have to consider those speeds, those velocities, in relativistic terms. And as we do that, we recognize that the momentum is mv over 1 minus v squared over c squared square root. So I'm just going to give you these relationships. You're welcome to go look up how they're derived, and you'll find that this will look familiar. This does look familiar, I hope, at this point. Now, as we've done with the other things, we want to keep in mind that as if we look at velocities that are much, much less than the speed of light, then does this really give us the classical physics relationship? And it does. So our understanding of momentum in sort of the world that we live in currently does tell us that momentum is mass times velocity, even when we consider the relativistic terms, because this ratio is so small, right? So at speeds much, much less than the speed of light, that's going to go to zero, and we'll end with mass and velocity. Okay, what about energy? Well, energy is in a similar vein, plus it has a little added coolness. So this is momentum, obviously. Now let's look at energy. We're going to look at energy of moving objects. Remember, all of this special relativity really had to do with looking at reference frames of something that's moving relative to something else, right? So we're going to look at motion. And we know that motion really is involved with kinetic energy. Okay, so that's going to come into play in our conversation. Now, Einstein found that the total energy, when we consider relativistic velocities, right, the total energy is equal to mc squared over the square root. I'm going to guess you know what this is going to say, minus 1 minus v squared over c squared. All right. So that's what we get. That is our total relativistic energy. Now, for low speeds, again, when the velocity is close to the speed of light, for low speeds, we find that the total energy is approximately equal to, and I'm going to use that, I'm going to tell you why in just a minute, mc squared plus 1/2 the mass times the speed squared. Now, if you solve for this relationship using what's called a process known as the binomial, that didn't sound right, the binomial expansion, when v, which we can use, we get this relationship. that's why it's approximate, okay? But what do we notice about this? Okay, again, this is the energy of a moving object. Well, first of all, we notice this lovely relationship. That's just our kinetic energy that we've already learned in classical mechanics. Right? It's our kinetic energy, 1/2 mv squared. But the cool thing is this term. This term of what we're going to call an object's rest energy. Now, why do I call it rest energy, or why do we? Not me. It's actually, as you might expect, E = mc squared. It's Einstein. This rest energy is the energy of the object even when it's not moving. It has energy, and that energy is related to its mass. I'm not going to go into a lot of detail about this in this sort of conceptual introduction to it, but this suggests that total energy has two pieces, a rest energy and this kinetic energy when that object then is going to be moving. This is really valid for low speeds, But what about all speeds or high speeds? Well, there's still a rest energy. If we think of this in terms of just sort of a generic relationship, this total energy idea can be written as the rest energy plus the kinetic energy. Rest energy piece, kinetic energy piece. So let's play with that idea. Let's think about that idea for a moment. At low speeds, this is our total energy. So what I'm going to do is I'm going to erase over here. I'm going to rewrite some things because we're going to use these equations differently for different particles, depending on if their speeds need to be considered in the relativistic term. Okay, so total energy we know is equal to the rest energy plus the kinetic energy. At low speeds, that's equal to mc squared plus 1/2 mv squared. Right? Where this is the total energy, that's the kinetic energy. At high speeds, when we cannot use the binomial expansion, but we can rearrange this relationship to look at two pieces. At high speeds, we also have this rest energy term plus, so this is just a mathematical factoring proof. So feel free to tackle that if you want or find it and look it up. We're not going to go through it. 1 over the square root of 1 minus v squared over c squared. That term just keeps showing up, doesn't it? Minus 1 times mc squared. So this is all. This is v much less than c, so low speeds. This is v on the order of c. Okay, high speeds. Now, when we look at objects moving at high speeds, these are things like electrons in radiation therapy or in a particle accelerator, where a lot of this idea of rest energy was proven. Again, go explore those concepts. They're fascinating and fun. If you have an interest in them, I encourage you to. But this is a cumbersome relationship. And so we're actually going to rewrite this variable, this part, as lowercase gamma. And we could write our time dilation experiment using lowercase gamma. We can, because this square root 1 minus v squared over c squared shows up in everything that we've talked about in terms of special relativity. So we'll often see the total energy written as this, okay? Just to simplify that expression. So what does that tell us? Well, this tells us, this again is our rest energy, but this term is now the kinetic energy of high-speed particles because we've considered the relativistic properties that happen at high speeds. Okay, so three relationships to think about. 2 different ways to think about kinetic energy. The classical one, which we can use this relationship all the time. Why? Because as soon as we're at low speeds, this turns into this when we remember that binomial expansion. But that's sort of our classic Newtonian mechanics, classical physics, kinetic energy. And this relationship becomes our total energy when it's important that we consider relativistic energy. All right, so you're going to have a couple of videos, one looking at an example of relativistic momentum, one looking at an example of relativistic energy. It's kind of fun stuff to think about. Good job.